So a car starts from a parking lot. A car starts from a parking lot and travels 1.2 kilometers. Which direction? South. And then turns apparently in the direction. Okay, you see, is this the good or the bad way of saying it? Bad way. Okay. So what does 53 north of east mean? If we do it in our good way, Amar, what would you say? East 53 north. Perfect. So it turns into whatever direction is 53, sorry, east 53 north and goes for further 3.1 kilometers in that direction. Relative or according to the starting point, which was the parking lot, where is the car now? What's the car's total displacement? Okay. So, okay, everyone, just so you know, what did we call the method yesterday? What was the name of the method we did yesterday? It was the cosine law. And what was the only reason we call it the cosine law? Is because you had to start with what? With the cosine law. You still need to do what at the end? Sine law. But because you start with the cosine law, I like to call it the cosine law method. Most books call it the what? Scale diagram. And that's actually why it's both not that popular compared to the second method, and I also don't like it because you need to sketch a what? What does scale diagram mean? It needs to be as what as possible? As accurate or precise as possible. But the problem is, I mean, you're not always going to have what rulers and protractors and so on. So that means what? Even if your distances are correct, but your what is wrong? Or if your angle is correct, but your what? Distances are wrong, what does that mean? You not just that, you are actually gonna get the what? The wrong answer. Because maybe instead of making your I'll give you an example. And actually that's the practice worksheet for today is imagine if you went, I'll show you. Everyone, imagine if you start here, eyes on here, and then you go here, and then you want to go this way. Problem is, if you don't sketch it long enough, if you sketch up to here, where's your final destination? Here, right? So you would think you went this way, but maybe you had to sketch what? Slightly longer. Where would you end up now? Do you see what I mean? Here, by the way, what's the direction of this? What's the direction of this vector? It's going what? North, but it's also going what? East. So it could be northeast or east north. How about this one? It's north what? Or, but do you see what I mean? Totally different direction. Do you see why you need to really be a good sketcher for this method? Because you really need to at least, at least exist in the right quadrant at the end. The second method I'm going to teach you today doesn't care if you even sketch anything correct. Okay? It will always guarantee that you end up in the correct quadrant. But that's why they call this one the scale diagram. You need to be a good estimator of angles and of also of distances as well. That's why we're only going to do it for the first time, and that's it. Okay, so let's go with what? Let's go with the diagram. All right. So obviously the diagram would look like this. So here's the parking lot. Which way did you move first? South. So that means, according to this regular compass, we go south. And again, I didn't even measure it. I just estimated to be what? 1.2 kilometers. Now, roughly speaking, how much is 3.1 compared to 1.2? See, that's what you need to be good with to really become good with this method, is estimating what ratios or scale differences between distances. 3.1 divided by 1.2, roughly, how much is that? How much? Almost half, or 3.1 would be what? Almost between double and triple, right? So what does that mean? Whatever you sketch from here has to be how long compared to this? Has to be between double and what? And triple of that, right? If you actually divide 3.1 by 1.2, you actually get more than 2.5. More than 2.5. So whatever you sketch here, if you're really scaling it right, should be 2.5 times at least that much. Okay, what was the direction again? Come on, what was the direction? East, how many degrees? So that means what? From here, by the way, always imagine, look everyone, always imagine you have a portable grid on you. Portable grid, look, everyone, eyes on me. And then you put it right here. Where's east? Which way? That way. So I'm going to put my hand like this and then go, how many degrees? 53. Which way? Up or down? Up, because north is this way. So my 53 is going to be below here, not up here. Otherwise, you're going to get the complete wrong answer. All right. So there we go. Does that make sense? East, 53 north. All right. So, by the way, that is not even 2.5, but at least you know we're going to end up somewhere there, somewhere for sure there. Okay. So our last, there we go. Does that make sense? Okay. Is this the right triangle? No way. So I can't use Pythagorean or what? I can't use SOHCAHTOA. That's why it's the cosine law method. Okay. How many sides do you know in this triangle? How many sides do you know? You only know two, obviously, because you need to find the what? The third. Okay. Do you remember when you always can use the cosine law? If you have what? If you have two vectors or two lengths, and which angle that you know? The one where? The one in between, right here. So if I have this one and this one, somehow I'm claiming that I know this one. Do we know it? Yeah, because that's the what? What was the name of the angle that makes this one 90? Complementary. What's complementary to 53? 47. Okay, so let's start. So we have, sorry, yeah, we're always so used to adding to 100. So you think 50, 47. Sorry, you're right, 37. Yes. Okay. Oh, that's nothing. I actually, apparently, okay, how many seconds in a minute? The problem is some people always think also in decimal. So when you tell them, for example, hey, what's 60% of a minute? They say, oh, that's 60 seconds. Well, that means that a minute is 100 seconds, right? Because we're so used to thinking what in decimal terms. No, that's 90 and that's 60. Okay, so let's do the calculation here. I think you have a slide for that. Yes, you do. All right, so I'm going to do my calculation here. So 37. Okay, let's name the vertices of the triangle. So it doesn't matter. Let's call this A. Or you can, by the way, you know that in math always, they always tell you use symbols or names that actually what reflect the problem, right? So for example, you can call this capital P for parking lot, and maybe this one, for example, like south, like S. But I don't want you to use S and east because those are legit names for what? For the compass. So let's just use ABC. A, B, C. All right. So what does that mean? Where's my small a? Lowercase a. Which one is it? The 3.1. Yep. Small b, the blue one. So apparently that's the one we're trying to find. And C is the 1.2. Okay, so let's do the calculation. So B squared equals what? Anyone? Finish the cosine law for me, Nura. A squared plus C squared minus AC, no squares. Cosine of small b or upper b? Yep, because angles are always capital. Good. All right. So let's do this. 1.2 square. Sorry. What's A? 3.1. 3.1 squared plus 1.2 squared minus 2. 3.1. 1.2 cosine of how much? 37 degrees. Question: is 37 degrees according to the cast rule from yesterday? Is it in quadrant 1 or quadrant 2? It's the small ones. It's between 0 and 9, so it's quadrant 1. Cosine of quadrant 1. All of them in quadrant 1 are what? Positive. So that means that negative will stay the same because that will be negative times positive, 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 positive. So they will not be able to what? To beat the negative. All right, good. So let me just end the show here or just I'm a big fan of actually when I have such a big complicated calculation, I'll start with the big part here. So I'm going to start with the cosine of 37. Make sure you're on degrees. So 37 trigonometry cosine times 2 times 1.2 times 3.1. So apparently after the minus sign, you should have 5.9418. Okay? All right. So equals sorry, what's three? So that's what? That's minus 5.9418. All right. I know that 1.2 is 1.44 when you square it, and I know or 3.1 is 9 point something. Yep, 9.61. 9.61. So if we add plus, sorry, let's do it. 9.61. You can keep going. This is just mechanical work now. 1.44 subtract 5.9418. 1471. So 71. What do I do with this number? Sure, you go ahead. I go back. Oh, was it? So what was the four-digit number? 5 point? Oh, okay. I trust you. I just want to see where I made a mistake. 37 degrees. Trig cosine it times 1.2 times 3.1 times 2. Oh, what, no, what do you mean by the whole thing? Oh, the whole thing in one shot. Okay. So, yeah, that doesn't make sense. 9.1 plus, oh, I made a mistake. You're right. That shouldn't be 14.71 because 9 plus 1 minus 5 cannot give you 14. Okay, so minus, sorry, okay, so 1 second. So I'll negate this plus 1.44. You see, I made a mistake without even knowing it. And if it weren't for you, I wouldn't have had to think about it. Yes, 5.1. Is that what people got? Yes, awesome. Thank you. 5.108. So 5.108. Yes. Okay, what do I do with this number? Square root it. So square root, you get b equals 2 point something, obviously. Square root is here, 2.26. Oh, what's the situation here? 2. So that should be 2 point what? 2.3 in kilometers. So the car moved what? 2.3 kilometers this way. Now, which angle are you going to give me? Remember, you have to always give me the angle at the start vertex. Where is the start vertex here? A. It's all, well, not always, but in this case, it's A. Okay, now what do I use? Which law? Sine law. Okay, let me open Microsoft Paint. It's easier. Okay, so 1 second. Okay, so sine A over A, sine B over B, sine C over C. Okay, what do we have here? We don't know sine A, so sine A stays the same. Of course, it's the one we want. What's A? 3.1. Okay. Do I know sine B? Yes, I do. And I just found out what B is. So sine of B, what's B? 37 degrees over 2.3. Okay. Crisscross. Crisscross. So 2.3 sine A equals, I'm not sure what that is, but there we go. Let's do 37 sine now times 3.1. 1.866. 1.866. Is this number, everyone, is this number smaller than this number? Yes, perfect. Which means what? When I divide, I'm going to get a decimal fraction, which is perfect because that could be what? Sine inverted. Otherwise, as we said yesterday, you can never get sine of bigger than 1 or cosine. So that means A equals sine inverse. I'm more than okay you jumping to this step if you like. You know you're going to divide 1.866 divided by what? 2.3, which in one shot, or I can do it in 2 steps here, 1.866 divided by 2.3. Trig. Second, you have to shift for second sine. 54.22. 54 2 degrees. There you go. Any questions so far? Make sense? Okay. How does this not agree with the diagram? How does this not agree with the diagram? Who understands what I'm asking about? Why does this not agree or sync up with the diagram? Josh? That angle, I don't care how crappy my diagram is this acute or obtuse? That's an obtuse angle. Obtuse angle is bigger than what? It's bigger than 90. What did we get? What answer did we get? 54. How many people remember the ambiguous case from doing the sine law in grade 11 function, or maybe even grade 12? Okay, everyone, listen up. Pencils down. 30-second explanation right here. Listen up, everyone. The sine law The sine law is weird. Why is that? Check this out. Let's go back, everyone. Let's go back to the cast rule. Let's go back to the cast rule. Noor, give me, I don't know, estimate this angle for me. Anything you want. Everyone, look here. 30, sure. 30. What would be then the mirror image of it still in the what? In the second quadrant. It would be still what here? 30. But that means the whole thing is how much? No, the whole thing. Yes, 180 minus 30, which is what? 150. Can someone go ahead? Go. Just the up to it. Okay, everyone. Sine of 30 is how much? By default, it's actually one of the famous angles, right? Sine of 30 is what? 0.5. Get me the sine of 150. Go ahead. Get me the sine of 150. It's not gonna be, nope. 1/2 as well. Look at it. What did I tell you sine is? Sine is always the y distance. Check it out. Do these two angles perfectly match up height-wise? Yes, they do. Do you see what I mean here? The sine law cannot distinguish between what? Between two angles that exist in quadrant what? 1 and quadrant what? It will give you the same what? The same sign, even though they are different what? They're different angles. Do you see what I mean? If you do, right now do sine inverse of what? If you do sine inverse of what? Of what? It will never give you what? It will always give you what? It never gives you the what? The quadrant 2 answer. It always gives you the what? Do you see what I mean? Calculators never give you the what? The quadrant 2 answer. They always give you the what? The quadrant 1 answer. That's why you have to have a diagram to what? To decide if this is the one you want or if this is the one you want. Is it making sense now? That's why it's called the ambiguous case. You don't know until you sketch a diagram. Awesome. Yeah. No, well, having fun. Yes. Art? Yeah. Sure. Yeah. Okay. Awesome. No problem. All right. Okay, so did that make sense? Now, everyone, question. How do I get from 30 to 150? You do 180 minus. So that means what? Is this answer, sorry, is the 54 answer correct or incorrect? No, the 54 degrees. I need a bigger angle than that. What do you just do? Every time you know you're supposed to get the what? The obtuse angle, just subtract 180 minus the answer it gets. Do you see what I mean? Because remember, what it gave you is the quadrant 1. You don't want a quadrant 1 angle. You want a quadrant what? Only because the diagram says so. That's all. All right, so let's do this. So the angle is angle A for sure. Yes, angle A. So, okay, everyone listen. So technically, could I call this now again A equals whatever? Well, here's the thing. Math teachers then would say, how come one angle equals two different values? Do you see what I mean? That's why they always tell you what, call this something else at the beginning, theta. And then if the theta becomes the A, then you just call it the A. If it's not, just say A equals what? 180 minus that. I don't really care about your notation. Just get me the right answer at the end. So you can go on the diagram and just say what? A equals 180. Subtract what? What was it? 54.2 degrees. How much is left? 100, 20, or 30? 25.8 degrees, which kind of looks like this. And what's the sig fig situation here? This is 4. We only need how many? 2. What is this to 2 sig fig? Is this closer to 120 or 130? Closer. It did cross the half point. So that means what? It's 130 degrees. Does that make sense so far? Okay. Does anyone have a question up to this point? Okay. There's one small trick here. Pencils down, everyone. Did I even write the final statement yet? Did I write the final statement? By the way, what do I mean by final statement? Come on. The displacement equals blah, blah, blah. Okay. Well, here's the final statement. Everyone look. Delta D equals, what was the distance? 2.3 kilometers. Bracket. Okay, everyone, eyes on here. Check this out. How are you going to report this angle? The question is, how would you report this angle? Because remember, you need to report it in what? North, east, southwest. Do you see what I mean? When you use southeast, northwest, that kind of stuff, the answer you have to use is less than 90 degrees. So which answer are we going to use again? 54. How can you, everyone, how can you measure this angle? Look, imagine that you have this line. So can someone tell me what the designation of this angle is? Anyone? Which way did you move first? And then which way did you turn? Just like we did yesterday. By the way, do you know what another way is to do this? Which way do you go first? No. South. And then how much did you turn? 130, but which way? Not north, east. Do you see what I mean? We don't want to do that. Imagine you split it right here and you just say what? You just say what? 54 degrees. Sorry, I mean east, 54 north. Yes. So say again? Uh, if you're gonna go north and east, you're gonna have to do the complementary. Oh, that's what you said? Yes. Everyone, you can either say, I'm gonna go east first and then turn up, or north, I guess, 54, or go north and then turn what? Turn east, 20 whatever, 28 degrees or 26 degrees. Make sense? I don't really care which way you start as long as the answer in the middle, like the sandwich number, is correct. So finally, my final answer is, sorry, right here. We said east, north. So east, north, 54 degrees. Yes. No, if I'm doing east, north. No, look. Oh my heavens, I forgot. Sorry, everyone. Sorry, I totally forgot. This is how much? This is how much, everyone? 90. So how much is left here? My bad. Sorry. No. That was a complete oversight on my part. How much is the whole thing? 130. How much is this stealing from it? 90. So how much is left? 40 degrees. My bad. Sorry. So sorry. Yeah. It's not this that we use. It's the full thing minus the 90. So how much? 40 degrees. Thanks, Josh. It's weird. The practice worksheet I'm giving you after this, not this one, the last one as a practice for like homework, is exactly that trick, which I completely overlooked. Sorry. Yes, Nora? Sorry, what did they say? Angle A, which is 130. Yes. Yes. Oh, it's this one. Yeah, that's the thing. It's always the supplementary. That's why you subtract it from, just like that. The supplementary is 30. So you just subtract to get the rest. Yes. Oh, yeah, sure. There you go. Go ahead. Yes, please. Yeah, apparently it's not given. Yeah, okay. Because we know our final answer should be what? Our final answer should be obtuse. But this is not obtuse, which means what? I am one step away from finding the obtuse angle. I just need to subtract 180 minus that. Yes, 100%. Again, I just proved to you. The sine law is what? Look, the sine law is completely blind to what? It's blind to being obtuse or acute. You have to actually what? Use a diagram to help you out. It will always okay. It will always give you the acute angle. It will never give you the what? The obtuse angle, because it can't cross that what? That 90-degree threshold. It's just how calculators are made. Okay. Okay. All right, everyone. Let's do the second worksheet of today. There we go. No more cosine sine law. This is going to be the most important method in the rest of the course and also for next year. Okay, so listen up. Let's now do the exact same problem we did yesterday, the plane going east and then veering off north 60 degrees east or something like that, the same worksheet from yesterday. But using what, everyone? But using the, that's just not working, but using, okay, this is called what? Vector what? How many people have heard the word decomposition before? When you decompose something, like in chemistry, when a not a molecule, a compound gets decomposed, what does that mean? Does it get built up or disintegrated? So that means what? Are you adding up or breaking down? That's why another name for this method is vector breakdown method. Vector breakdown method. Okay, everyone, this method has an amazing feature to it. Even if you forget the cosine law and the sine law, you're still 100% okay. This method completely skips over cosine and sine law. Okay? So, and that's why it's so much a favorite between so many students. So this actually is the standard or conventional method for combining vectors, especially in first-year physics and math as well, when you take like vectors. Okay, everyone, step number one in this method. Number one, move all vectors to the what? Do you remember how we sketched the diagram yesterday for the plane? First, we sketched the diagram of the plane going which way? Which way? East. And then where did you put the second vector? Back at the starting point or picking up after the first one ended? Who remembers? Was it again at the same starting point or did it start where the first one ended? It started where the first one. This one is the opposite. All of them start where? At the same what? They all start exactly at the same starting point, which is going to be the origin of the XY axis. Okay. Number two. Number two. Decompose or break down the vectors into what? Into two perpendicular components. Two perpendicular components. Number three. Number three. Combine vectors on what? On each axis completely by itself. So basically, everyone, eyes on me, you basically break your problem into how many dimensions? Into how many? Two. Or if you had 3 dimensions, you would break it into what? 3. Don't worry, we do not do 3D in grade 12 physics, and it's even barely done sometimes in first year. But we're gonna focus on what? 2 dimensions. So basically, you're gonna break down all the vectors into either being on the what? On which axis? The x-axis or, and that's it. The x-axis is treated by itself, and the y-axis is also treated by itself. Okay? All right. So let me show you basically why this method works all the time. Everyone, eyes on the screen. Let this actually sink in. Imagine, everyone, don't copy. You don't need to copy this. So imagine if you walk or if some object moves this much in this direction. Okay. Again, let this sink in because this will prove to you that the two methods are really the same. And then once it's done this trip, oh, sorry, it moved here. By the way, that doesn't mean it jumped here. It just means it moved in this direction this much. And then it moved this much and then this much. How many trips are we talking about? 4. Are they numbered? What does that mean? Which one happened first? Trip 1, and then 2, 3, 4. So they are in sequence. What does that mean? Let's actually put them in sequence. Let's actually move them so that whenever trip 1 ends, what begins? And so on and so forth. Okay. So do you see what just happened? What did I do with the vector? I just what? I just shifted it, right? Did I change its direction? Did I change its length? What did I just change about it? It's location. When you change location with vectors, everything is okay. You just can't change what? You just can't change what? Size or length or angle or direction. You can change location. All right. What should I put at the end of the blue arrow now? The beginning of the red arrow, yes. And then finally what? So if you started from here, like even if I did it in the classroom, I move this way, and then this way, almost 90 degrees, and then I go back, and then where would I end up overall? How much is just my displacement? Is it a big displacement or a small one? Seems to be a small one, because all you care about is I just moved from here to where? To here. Does that make sense? Okay. So we agree that this black arrow is the what? Is the overall displacement. Okay? All right. Let's do it with the method I want to teach you right now. Okay. Oh, interesting. What did I do with the numbers? Are they the same or different ones? Guess what? You're still going to end up the exact same spot. Look. Are these two the same vector? Yes, they are. Okay? So adding vectors is like adding numbers. It doesn't matter which one goes first. Okay? As long as it's the exact same displacement at the end of the day. That's fine. Okay. All right. By the way, does this even make sense even with simple ones? Yeah. Okay. Tell me to move 3 steps that way. Go ahead. 3 steps which way? To you. That would be what? East. So 1, 2, 3. Okay. Now tell me to move what? 3 steps that way. To you, that would be what? To me, yeah. To me, that's north, but to you, that's south. 1, 2, 3. I end up here, right? So my overall is from where to where? From there to there, right? If I flipped my motion, would I end up exactly at the same spot? Yes, I would. Look, what do I have to move now? And then, did I end at the same spot? What does that tell you? Adding vectors doesn't need to be ordered. No, just add them somehow. Just make sure you do not overcount or undercount. Okay, nice. So check this out now. It's the same. Okay. Okay, look, everyone. Here are my vectors, and I couldn't care less if they're numbered or not. I just need to consider them all. All right. Now let's do this. Can someone see how this one is going to be broken down? Can you tell me what 2 vectors are the breakdown vectors of this one? By the way, this one points in which direction? This one, that one, points in which direction? East, north, or northeast. So that means one vector, one decomposition has to go which way? And one vector has to go? That's it. Look. You see it? Where's the first vector? This much. Where's the second vector? That much. Question for you. What kind of a triangle is that? A what? A right triangle. We're back again to what? So, ka, to what? Do you see what I mean? That's why this method is much easier than what? Than the cosine sine law. It doesn't need a good sketch. It doesn't need a scale. Even if your angles are busted, who cares? Just stay in the what? Just stay in the correct quadrant for each vector and you're golden. Okay. Can I apply the same method to all of them? Can I apply the same breakdown to all of them? Yes. Imagine you have a portable grid and you just keep, you do it here, you do it here, you do it here, you do it here. All right. So let's do that. Next. Next. How many original vectors did I start with? But each one gave me how many copies or how many shadows? 2. A vertical shadow and a what? And a horizontal shadow. So how many vectors am I just going to consider now? 8. But those 8, are they angled or just perfectly perpendicular? Exactly. So think about this way, everyone. Now, you didn't even need to look at the original one or this one or this one or this one. You can look at the what? You can look at the what components? The perpendicular components. Yes, go ahead. Thank you. Perfect. What if one vector is already what? perfectly on the what? On the what? On the x or y. Technically, could it still be broken down? Yes, but one of the components would have size what? Is it making sense? It's still the same thing. But now you actually have an easier job with one of them because one of them doesn't have a what? A shadow on one of the other axes. Is it making sense? Still 100%. Okay, it's a freebie. By the way, I have a habit of calling what? Good vectors, like vectors already on the axis, I call them good. Any tilted vector, I call it what? Bad, because you need to what? You need to shadow twice. Okay? All right. Perfect. So check this out, everyone. Now let's add them up. Look, here's the proof that it's still going to end up the same way. All right. Are those the tilted ones or the children? Those are basically what? The product, the decomposition. Okay, what do I do now? I'm going to take the horizontal ones. I don't care which one you take first. Let's take the horizontal ones. 1, 2, 3, 4. Okay, let's line them up. Look. Does that make sense? I lined them up on their own dimension. Everyone, if you walk this much, and then you walk this much, and then I walk this much, and then this much. Overall, how much did I walk from my starting point? From here to here, right? That's it. So the overall of this is from here to here. All right. Oh, sorry. Okay, fine. Let's do the other one. What's the overall for that one? Just what? Just a small one? Exactly. One small step down. Is that green one the exact same old, short, black one? 100%. It's the same thing. Now, I know what you're thinking. Trust me. Why do all this, right? Why can't we just do it that way? Two reasons. Number one, that method, when you do cosine and sine law, what do you start getting? Exact or approximate numbers. Boom. And they're bad approximate, right? Because you could actually have big, big errors. That's number one. Number two, whenever I gave you the cosine sine law, how many vectors did you need to add up? Two. How many vectors did I give you here? The original ones. Can you add 4 vectors using the triangle method? No, you can't, because a triangle has how many sides? 3. Everyone, if I give you 4 vectors, you have to do the cosine sine law method how many times? 3 times, because you have to add vectors number what? Number what? 1 and 2. Get that result, add it to vector number what? No, just you already used 1 and 2 to build what? A resultant. You take that resultant, you combine it with vector what? 3. Just 3. You take that resultant, you combine it with vector what? But every time you're doing that, you're using the cosine sine law. So every time you're doing it, you're introducing what into your system? Error, approximation, and all that. Do you even need to worry about that here? Nope. You just need to worry about breaking them down how many times? Just what? Just once, and then doing x's and y's together. That's the whole idea. Okay? Okay. So the other reason is what? I will almost never give you just how many vectors to add. I will usually give you what? Or, yeah, if you do it with the sine cosine law, you are introducing error. By the way, the diagram for 2 could be tricky. Imagine the diagram for what? Or it gets worse every single time you make it. This one is the what? Is the most exact one or the most accurate one for what? For more than 2 vectors. Okay? More than 2 vectors. So what does that mean? If I give you 2 vectors, I'll leave it up to you to use this method or the other one. If I give you more, you have got to use the what? The other one. Oh, right. Okay. So let's do the question you have. I bet. Okay, come on, let's start. So, did I give you the worksheet? Yes. Good. Okay. Question. How many vectors do we have in this problem? Come on. How many? 2. Are they still the same vectors from yesterday? Come on, guys. How many? Yes, they are. Okay, but this time, how do we sketch them? Starting from the end or starting from the same starting point? So that means what? Instead of sketching this guy and sketching one here, what am I going to do with it? I'm going to what? Exactly. I'm going to move it right here. You got it. Okay, so let's do this step by step. So there we go. Go ahead. Oh, you need protractors? Just give me 1 second. Protractors? Back off. All right, sure. Just, oh, okay. Gotcha. Come on. Okay, yes. Oh, rulers? Oh, I just, okay, yeah. Rulers? Skip to each group. Come on, come on. Who needs a ruler? Yes, yes, it has to be. By the way, only today. It has to, so it has to be 60 exactly, everyone. This has to be 60 exactly. This has to be wherever 65 ends, and this has to be exactly as long as a 50 right here. So just measure how much you need a 50 here, and just go do it on the 60-degree line. Yep. Yeah. Again, use the scale that you know to use it to measure a 50 kilometer. So measure 50 here, and replicate it right here. What's up? Yep. So measure it here. Just memorize the number for it, and then just extend this for as long as you need.
It goes all the way.
No, no. You just need 50 replicated here. That's all. Because it only moves 50 that way. Who's done? Just give a minute. Okay. How many vectors do you see? How many bad vectors do you see? How many good vectors do you see? This is a good vector because it's what? It's already on the what? It's already on the x-axis, the horizontal one. But this one is what? Bad, because it needs how many decompositions? 2. Where are they going to be? They're going to be this much and this much. Okay? So go ahead on your diagram. On your diagram, right there. Come on. Nothing. I just added what? I just basically showed you, Janelle. I just showed you that if you project or drop it this way, it would cover this. If you, everyone, listen up. The word projection in math means what? Means shadow. So everyone, listen up. If you have a flashlight and you shine it here, where's the shadow? If you shine it here, where's the shadow going to be? Right here, right? Make sense? What if you shine it here? Where's the shadow going to be? That's the whole idea. Imagine a flashlight and you're just projecting on the X, sorry, the Y or the X. Yep, it's always shadow, always shadow. 1 second. Oh, you just need this part. You just need this part. Come on, come on, come on. I want to show you the math of it because it's really easy. What's up? Yeah, yeah, you're good. Yeah. And I didn't want you to, well, technically, this has to be perfectly parallel to this guy. That's the whole idea. By the way, everyone, what am I making here? Am I making a full rectangle? Yeah, that's the whole idea. You're making a full rectangle such that, listen, two of the sides are shaded. Sorry, not shaded, dotted. And two of the sided are on the X and Y axis. That's how we're going to do it every single time. So now I have a question. If I want to get this one, if I want to get this much, would I use sine or cosine? Okay, let's label. What do you call the diagonal, or what do you call the longest side in a right triangle? Okay, so this 50 is the what? Is the hypotenuse. Do I have an angle given to me? Great. So katoa is about to be used. If I want this guy, this is what to this? Opposite or adjacent? This one. It's adjacent. What do you use with adjacent? Sine or cosine? So katoa. So that means what? If you want to find this one, you have to use what? Cosine. What if you want to use, sorry, what if you want to find this one, which is the same as this one? This is what? Opposite. What do you use with opposite? No, no, you're right. So sine. So which one are we not going to use now? Remember, yesterday we used tan. Today we use what? Sine and, because I need the what? I need the two perpendicular shadows. All right, let's do that. By the way, everyone, I want you to resketch this quickly. Just 1 second. Everyone, listen up. This right there, you can sketch it right here. Because now we're about to do the math. All right? Oh, actually, everyone, you don't need to. If you're content with the size of your rectangle on your sheet, on the part A, you're fine. So let's do the math here. How many people agree this is correct? This is nothing but SOH. Do I know this? Can I calculate this one? Do I know this one? Can I calculate this one? Crisscross. Let's do that. By the way, again, there's an invisible one. Okay. Can I do the same thing now with the cosine? 100%, same amount of work. But now I'm going to get the short edge. Or I should say the horizontal edge. All right. By the way, just so everyone, question. Question. Am I even, so far, am I considering both vectors or just the bad vector? By the way, I'm just trying to break down the bad vector. The good vector does not need to be broken down because it's already fully on the x-axis. So I'm just operating on what needs to be broken down. By the way, everyone, this part, listen up. This part should only take, ready? Everyone, this part, eyes on me, everyone. This part should only take no more than the first half of the solution space for part B, because we still need to what? Finish the question in the second half. Okay, so I don't want you to spread it way too much. Yeah. Everyone, the final slide is coming up after this. Okay, so one slide left. Okay, who's done? Who's done copying the breakdown? Who's still working? Okay. By the way, I'll be the first one to say, listen up. I'll be the first one to say that for two vectors, like for a two vector addition, this method is overkill. You'd rather use what? The other method, the scale diagram or the cosine limit. But when you jump to what? Three vectors or more, oh, that becomes overkill. This is the way to go. You'll see much more tomorrow. Okay, let's go to the next slide, everyone. Next slide. Oh, so I already labeled them on my diagram. Okay. What did I just do here? By the way, don't put this on your diagram. Put this, everyone, put this in your solution space for part B. Does anyone know what I did in the first line? What did I say? Overall what? Yes, because 65 kilometers came from here, and how much came from the other vector? 25, the adjacent, the small one. So overall east, the plane moved 25 plus 65, or 65 plus 25, who cares? Which is 90 kilometers. Overall north, it just moved how much? Overall north, how much? Which only came from this what used to be a bad vector. I always want you, once you know the overalls, to sketch a quick box like this. Can someone tell me where the diagonal of this is going to go? The diagonal of that, how is it going to go? Yes, it's going to go that way. That's, yeah, go ahead. That's my overall displacement. There we go. Okay, everyone. So your diagram should always look like this. Well, not always, for two vectors. All right. Look how detailed I went in my what? You don't have to be that detailed. But when I post this, everything should make sense. What does D2y mean? What does D2y mean? Distance 2 on which axis? It's the what? How much? How about, so this is D2y. What was before? Oh, before there was what? D2 what? By the way, you don't have to actually do it this way, but this is the most organized way to do it. And then what did I do? What does this mean? D on the what? 1 plus 2x, which is how much? Is there a need for addition here? No, because one vector was purely on the x-axis. Sorry, on the y-axis. Thank you. So what do I do now? I do this. The plane moved overall 43.3 up. Sorry, not up, north. And 90 kilometers which way? East. By the way, do you notice which angle I always want you to give me? The horizontal or the vertical? Please always give the horizontal angle. Always give the angle with respect to the x-axis. Why? Because it's always the way to actually give angles in math and physics. Always give the angle with respect to the x-axis. No, sorry, no, they're not equal. They're only equal if those two are equal, right? But you could say they're consistent because those two add up to 90. That's the whole idea. What theorem am I applying here? What is this? Pythagorean theorem. But I'm doing it what? In one shot. I'm already doing the what? I'm already doing the what? The square root. Is that the same answer we got yesterday? Yes, it is. Okay, why am I using tan? Look, because I already have my adjacent and I already have my opposite. So I am trying to get this one I don't want to use my hypotenuse. I want to use the last two I got. Is that the same angle we got yesterday? Yes. Same answer. Yes. Yes.
Why did we put 43.3? We already have the destination here. Why
Yes.
did we put 43.3? We
No,
already have it at 50.
no, because okay, Hail, this 50 is only for one trip. Remember, the plane actually is gonna move this way overall. Because remember, this used to be here, right? This used to be here, correct?
Yeah.
So the plane is actually gonna end up moving this way, like from yesterday. So that's why I still need to know how much it moved here and how much it moved overall here. That's why. Okay. And that's it. Okay, so that's how we do the decomposition method. Did we use sine law? Did we use cosine law? We just use what? So, ka, toa. We use so, ka to break down the vectors, and we use the tan to find the angle backwards. Welcome to the decomposition method. This is going to be used for the rest of this unit, for forces, for almost every single other thing.